Good afternoon, students. In the previous class, we have learnt the periodic table classification into four different blocks. Okay, S, P, D, and F blocks. So today we shall discuss about general characteristics of transitional elements. Okay. Now, first general characteristic we have already completed in the previous class, that is atomic and ionic radii. Okay, decreases along the period. Now let us start from the second characteristic property. Alright. Ionization potential and electronegativity changes slightly along the series. So when you move from left to right along a period in the periodic table, ionization potential and electronegativity slightly change. Now in order to understand this, you must know what is ionization potential and what is electronegativity, which you already learnt in your PU classes, right? Now, what is ionization potential? It is nothing but the energy required to remove the outermost electron in isolated neutral atom, isolated neutral gaseous atom, alright. And what is electronegativity? It is the relative tendency of an atom to attract shared pair of electrons towards itself, right? Towards itself. So, this change, decrease in the atomic size, why they change? Because due to the decrease in the size, atomic size, and increase in the nuclear force of attraction. You know that along a period in the periodic table, the atomic size goes on decreasing, right? Because effective nuclear charge increases, or in other words, nuclear force of attraction increases. Okay. So when the size is small, force of attraction by the nucleus on the outermost electron increases. Therefore, size shrinks, or shrinking of size takes place in the atoms present in this series. Okay. So ionization potential as well as the electronegativity change slightly along the series, right? Now we shall move to the next slide. Okay, that is third point. So in this we will study about the variable oxidation states, right? Now variable oxidation states depending on the number of electrons participating in the bonding. So variable oxidation state depend upon the number of electrons. Okay. They participate in the bonding. Example, manganese shows oxidation state of +2 in manganese sulfate. Alright. So manganese sulfate, what is the charge of sulfate? -2. Correct. So manganese is having +2 charge, or oxidation state of manganese is +2. Whereas in the case of potassium permanganate, you can see the permanganate molecule. Okay. Potassium permanganate, the molecular formula KMnO4. You can find out the oxidation state. Okay. So oxygen having -2 charge, so -2 into 4 is -8. Potassium is +1, therefore manganese is +7. Okay, +7, manganese +7, potassium +1, oxygen is -8. Alright, therefore manganese is having +7 charge in potassium permanganate molecule. In the case of Mn2O7, that is manganese heptoxide, what is the oxidation state of manganese? Oxygen is -14, because -2 into 7 is -14. Therefore, manganese must be +14. +14 means 2 atoms are there, Mn2, right? Mn2. Therefore, +7 into 2. Therefore, in both the molecules, that is KMnO4 and Mn2O7, the oxidation state of manganese is +7. Alright. Now next example is titanium. Titanium has oxidation state +2, +3 and +4, right? Vanadium has oxidation states +2, +3, +4 and +5. Okay. Now we shall move to the next slide, fourth point, that is the fourth general characteristic. Transition elements and their compounds are used as catalysts in several organic and inorganic chemical reactions. So most of the organic and inorganic chemical reactions, these transition elements are used as what? Catalysts. Now a few examples are given here. Iron is used as a catalyst in the manufacture of ammonia by Haber's process. So in the Haber's process of manufacture of ammonia, okay, so which transition element is being used? Iron is used as catalyst. And what is the equation for that? Nitrogen plus 3 hydrogen gives what? To ammonia, correct? To ammonia. And which is the catalyst used, or which is the transition element used? Iron is used as catalyst, right? So transition metals or transition elements are used as catalyst in most of the organic and inorganic reactions. Now you see the another example. Nickel used as catalyst in the hydrogenation of oils. Okay, so oils react with hydrogen, or in other words, hydrogen gases pass through oils. What is the physical nature in at room temperature? Liquid nature, right? So liquid oils, through liquid oils, what are going to pass? Hydrogen. Okay, in the presence of nickel. Nickel is the transition element, correct? It is the transition element. So you can convert into fats. Fats are most probably in which physical state they exist at room temperature? Solid state, correct? So then by this process we can convert liquid oils into what? Solid fats. Okay, best conversion of liquid oils into solid fat by passing hydrogen in the presence of nickel. Okay, nickel is the catalyst used, and it is the transition element. Alright, now we shall see the another example. Platinum is used in the manufacture of nitric acid by Oswald's process. Okay, here only one equation is given. All the equations of manufacture nitric acid not given. Okay, the equation where or in other words the reaction where we consider the transition element as the catalyst, only that equation is given. Alright, so 4 ammonia molecules combined with 5 oxygen, okay, and which is the transition element is being used here? Platinum. So to give what? Nitric oxide, 4 molecules of nitric oxide and then 6 molecules of H2. Okay, so these are the 3 examples, or in the simplest examples I can say, to indicate transition elements okay, used as the catalyst. We shall move to the next slide. Fifth point, most of the transition elements are metals which are hard and have high melting points and higher boiling points and low volatility. Okay, most of the transition metals have got hard, they are very hard, therefore they have got high melting point. Since they are hard, you need to heat it to a very high temperature, right, in order to melt it. Therefore they have got high melting points. Okay, even boiling points. If you convert into solid metal into liquid, and then you have got to boil, right? That is the boiling point. So the higher boiling point is also required. Then volatility, low volatility. They are not volatile in nature. Okay, they are, in other words, they are very low. They have got very low volatile nature because most of them are metals, right? Metals, so they are less volatile. So examples are given, 3 examples are given in this slide. Chromium, okay, 3D element, 2148 Kelvin. You can see the temperature, very high temperature, 2000, okay, 148 Kelvin. Even molybdenum, that is the example for 4D series, right? 4D series example, molybdenum. What is the temperature? 2883 Kelvin. Tungsten, 5D element, right? 3000. So it is having highest, okay, highest temperature, that is 3683 Kelvin. Now 6th point, coming to the 6th point. They readily form complex compounds or coordination compounds. Transition metal ions combine with a large number of ions or molecules ligands to form what? Metal complexes. This coordination compounds, the basic coordination compounds you have already studied in PU classes, right? So simplest examples are being given here. Potassium ferrocyanide, what is the formula? K3FeCN6, alright? Which is the transition element present over here? Iron, Fe, which is the central metal atom, correct? And which is the ligand present over here? Cyanoligand, Cn, okay? So ligand is cyanoligand, okay, 6 cyanoligands are there. Central metal atom or metal ion is iron, okay? What is the name of the compound? Potassium ferrocyanide, okay? So that is the complex compound, okay, with one transition element. Similarly, nickel tetracarbon, this is another complex compound, okay, transition metal complex compound, which is the transition metal present over here? Nickel, okay, which is the ligand present over here? Carbonyl ligand. How many ligands are there? 4 carbon ligands are present. So, or in other words, okay, transition metal ions also form complex compounds. So we shall move to the next slide now. 7th point. they have low atomic volume and have high charge density. Atomic volume is very low, therefore they have got high charge density. What is the formula for density? Mass by volume, right? Correct. Density is equal to mass by volume. Low volume means volume comes in the denominator, correct? Volume is in the denominator, therefore if volume is less, then density will be more, because density is equal to mass by volume. Therefore since they have got low atomic volume, the transition elements have got high, very high charge density, correct? Now 8th point, most of them are paramagnetic in nature. So most of the transition metals are paramagnetic in nature. That is, the magnetic property is shown by what? Transition metals. You know that there are three ways of explaining this magnetic property: paramagnetic, diamagnetic, and then ferromagnetic. Okay, so these are paramagnetic in nature. Transition metals and the compound exhibit magnetic properties due to the presence of partially filled d orbitals. So you know that all the transition metals, okay, they have got partially filled on d orbitals, right? So partially filled, because of the presence of partially filled d orbitals, they show on magnetic properties. Okay, so one example is cupric ion. Okay, cupric ion, what is the electronic configuration? I mean outer electronic configuration 3d9 4s0, right? 3d9 4s0. So it has got one unpaired electron. Okay, if you write the 3d configuration, there are 5 d orbitals, right? So 2 into 4 is 8. So 4 of the orbitals have got paired electrons, or 2 electrons in other words, correct? The last d orbital will contain only 1 electrons, 8 plus 1, correct? So it has got unpaired electrons. Since it has got unpaired electron, it shows one magnetic property, and magnetic moment is 1.73 Bohr magneton. Hence it is paramagnetic. So it has got one unpaired electron, therefore it is paramagnetic in nature. And what is the value of magnetic moment? 1.73 Bohr magneton. Okay. Then cobalt nickel ion have got high paramagnetic behavior. So cobalt, nickel, iron, all are one transition elements. Once again, they are all called one ferromagnetic substances. Okay. So next slide, 9th point. Most of the transition elements and its compounds are colored. You must know that most of the transition elements are colored in nature. Okay. So for example, copper sulfate is blue in color. Okay. Cobalt chloride solution is red in color, right? Red in color. Why these complex compounds show color, or why they exhibit color? Because of DD transition. What do you mean by DD transition? The electrons, partially filled electrons, which are present in the d orbitals, okay, they absorb wavelength, okay, particular wavelength, and then they get excited, and then they come back to the original orbital. Okay, original orbital they come back. So when they come back, they emit radiation of some other wavelength. Okay, some other wavelength. Therefore that radiation will be given in the form of one color. Okay, so copper sulfate white is blue in color because it absorbs red wavelength. So red color of that wavelength range. Okay, therefore it will emit blue range. That means blue wavelength range. That's why it appears blue in color. Okay, similarly cobalt chloride red in color. White is red in color. It absorbs wavelength of blue region. Okay, so while get excited, electron get excited from lower to the higher orbital. Okay, it will absorb blue color, and when come back it will emit red radiation, okay, or wavelength of red range. Therefore it appears what? Red in color. That is known as DD transition. Alright. Next point, 10th, they have non-stoichiometric compounds or interstitial compounds. So these compound transition elements form non-stoichiometric compounds or interstitial compounds. Examples given are iron hydride, Fe3H. Okay. So Fe3H, ferric hydride, titanium hydride. What is the formula? Titanium hydrogen 1.70. So they can form non-stoichiometric compounds or interstitial compounds. So these are called interstitial compounds or non-stoichiometric compounds. 11th point or 11th characteristic. Okay, transition metals form number of alloys with different composition, different properties and different applications. Okay, they form number of alloys. What do you mean by alloys? One metal can combine with other metals, okay, in traces, okay, or in some proportion I can say. Okay, so stainless steel is one of the alloys of iron. You must be knowing that, right? Most of the utensils are made up of what? Stainless steels, which are durable, right? Which are very durable. They are used as utensils. So example, stainless steel, okay, which are the elements present in stainless steel? Chromium, nickel, iron, carbon, okay. Chrome steel, once again another alloy. What does it contains? It is also a alloy of iron contains. That means, what do you mean by alloy of iron? Majority will be iron, and in traces what will be there? Other components will be there. For example, chromium and carbon, okay. So we'll move to the next slide. Stabilities of oxidation states. Now we shall see here stabilities of oxidation states. Transition elements show variable oxidation due to the electronic configuration. Now, why all these transition elements show one different oxidation states? Okay, very few elements give only one oxidation state. Most of the majority of the elements give one different one oxidation states. And what is the reason? That reason is due to their electronic configuration. Okay, due to their different electronic configuration, they show variable oxidation states. The less common and unstable oxidation states are given in the bracket. So here is a tabular column, okay, of 3D series. You can see here the unstable oxidation states which are given inside the brackets. Okay, most stable are given as it is, okay, without the brackets, and only unstable are given in the brackets. You can see here in this scandium, okay, first element +3, it is the most stable one. Titanium +2 is given in bracket, that means unstable. Okay, stable oxidation states are, which are the stable oxidation states? +3 and +4. So stable oxidation states are +3 and +4. Okay, and vanadium there are 4 oxidation states. All are stable, right? All are stable. Which are those? +2, +3, +4 and +5. All right. Chromium on the other hand, which are the stable oxidation state? +2, +3 and +6, right? +4 and +5 are given in what? Bracket, therefore they are unstable. Only in very few compounds it might be having, but they are unstable. Manganese +2 and +4, +7 are stable one, correct? And unstable one are +3 and +6, okay? Iron on the other hand, +2 and +3 stable, +4 is one unstable. Cobalt, okay, cobalt +2 and +3 stable, +6 is unstable, okay. Nickel +2 is stable, +3, +4 are unstable. Copper +1 and +2 is stable, okay. What is that +1 called? Cupric form. +2 is called cupric, right? +2 is cupric, cuprous is +1, correct. Zinc +2, okay, zinc +2. So this is about 3D series, okay. So we shall move to the next slide. 4D series, okay. Yttrium +3. So you can see all the, I am not going to read all this, okay. You can find out that the stable oxygen states are given without the brackets, and unstable one are given in brackets, okay. Yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, and then cadmium. Next, similarly in the 5D series, lanthanum to mercury, right? So stable one are given in without brackets, and unstable one are given in with inside the brackets, okay. So next slide. The stability of particular oxidation state depends upon the nature of the element with which a transition metal forms the compound. So stability of particular oxidation state depends on what? Nature of the element, okay, with which a transition metal forms the compound. So it depends upon the nature of the element with which it transition metal forms the compound. The highest oxidation states are found in compounds of fluorine and oxygen, okay. Highest, when transition metal combines with the fluorine and oxygen and forms the compound, then it shows highest oxidation states. And what is the reason for that? This is due to high electronegative values and small size of fluorine and oxygen, okay. You know that the electronegativity values of fluorine and oxygen are very high, right? Fluorine is very small size, okay, high electronegativity value. Even oxygen has got small size and having high electronegativity value. Therefore, any metal, transition metal combines with these elements shows high oxidation states, okay. So next slide. The variable oxidation states of transition elements are because of the participation of ns and n-1 d electrons in bonding, okay. Why they show variable oxidation state? Due to the participation of ns orbital. N means last outermost orbital, ns orbital, and then n-1 d orbital, correct. Electrons present in n-1 d orbital. So these are involved, therefore they show variable oxidation states. Lower oxygen states in general are exhibited when Ns and N minus 1 d electrons participate in bonding. Okay, so lower oxidation state in general are exhibited when Nes and N minus 1 d electrons participate in bonding. So next line, the stability of maximum possible oxidation number decreases across the period. When you move across the period, the maximum possible oxidation state stability, what happens? Decreases. Consider the stability of oxides of vanadium, chromium and manganese. If you consider the stability of vanadium, chromium and manganese, oxides of vanadium, you can see here formula V2O5, okay, and vanadium dioxocation VO2 plus, they are used as what? Mild oxidizing agents. Another example, chromium CrO4 2 minus, okay, or Cr2O7 2 minus, and manganese 7 as MnO4 minus, okay, are powerful. They are used as powerful oxidizing agents. So they are not stable in the presence of reducing agents. So any compound which is stable in the oxidizing agent, it will be one not stable in the presence of reducing agent. The most stable oxidation states of each element of first transition series are given here. Scandium, okay, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc, okay, copper and zinc. So next slide, salient features of oxidation states of transition elements. Now what are the salient features of oxidation states or important features of oxidation states of transition elements? First point, in each group highest oxidation state increases with increase in the atomic number, reaches maximum and then start decreasing. Example has been given in the first transition series, which is the first transition series 3D series. Maximum oxidation state is shown by one manganese, that is +7, right? So each group highest oxidation state increases with increase in atomic number, reaches maximum and then start decreasing. So here manganese is present in first transition series, that is 3D series, okay. So it will show highest oxidation state, which is that manganese +7, alright. Second point, the transition element in lower oxidation states, which are the lower oxidation state, +2 and +3. The highest will be +7 usually, okay, +7, and which element shows manganese. So the lower oxidation states are +2 and +3 normally. So generally form ionic bonds, okay. So the element which shows lower oxidation state shows generally which bonds? Ionic bonds, okay. Example, ZnCl2. ZnCl2 ionizes into Zn2 plus and then 2Cl minus, correct? So this is an ionic compound, okay. So Zn shows +2 oxidation state, which is the lower oxidation state. So compound, it forms ionic compound, okay, or ionic bonds are present. Higher oxidation states, bonds are covalent, okay. If any element shows higher oxidation state, then the bonds present in that molecule are covalent, okay. In chromate ion CrO4 2 minus, right? Formula is 2 minus, CrO4 2 minus. Bonds between chromium and oxygen are covalent. So this is a covalent molecule. So bonds present in chromium and oxygen are covalent, right? So with this I will stop here, okay. So please go through the slides, okay. Any difficulty, any doubts, please clarify with me. Either you can contact me or meet me in the department whenever you are coming to the college, right? So next class I am going to continue the next salient features, okay. Thank you.